Hi everyone, welcome to today's webinar, Developing Clarity, Applications of Direct Detection for Electron Backscatter Diffraction. Before we get started, I'd like to review the process of submitting questions. To submit questions, you do it all through the questions pane on the right side of your screen. Any issues regarding connectivity during the webinar will be addressed immediately, and any questions for the speaker will be answered at the end of the presentation. If we don't get to your question today, we will answer you via email after the webinar. I'd like to introduce today's speaker. Matt Nell is the EBSD product manager at EDAX and has a passion for EBSD and microstructural characterization. Matt joined TechSem Labs, known as TSL, upon graduation from the University of Utah in 1995 with a degree in material science and engineering. At TSL, Matt was part of the team that pioneered the development and commercialization of EBSD and OIM. After EDAX acquired TSL in 1999, he joined the applications group to help continue to develop EBSD as a technique and integrate structural information with chemical information collected using EDS. Within EDAX, Matt has held several roles, including product management, business development, customer and technical support, engineering, and application support and development. Matt has published over 70 papers in a variety of application areas. He greatly enjoys the opportunity to interact with scientists, engineers, and microscopists to help expand the role that EBSD plays in materials characterization. In his spare time, Matt enjoys playing golf and pondering if changing the texture of his clubs will affect his final score. Now over to Matt.
Thanks, Jonathan, for that introduction, and welcome everyone to this webinar. Just as a little review outline of what I'm going to talk about today, I'm going to review direct detection technology and how it applies to EBSD, talk a little bit about the sensitivity of direct detection and how it brings increased performance and capability, both in terms of low beam current performance and low beam energy performance. Then I'm going to show some examples of using this sensitivity on beam sensitive materials like Perovskite solar cells and some biomineral applications. Then I'm going to show some result of linking direct detection and using EBSD pattern simulations for pseudosymmetry analysis. And before I get going, I'd really like to acknowledge a lot of people who have helped compile this work. My colleagues here at EDAX, Renee Declos, Stuart Wright, and Will Lenthy, Ming Pan at Gatan, the Perovskite group at the University of North Carolina, and Josh Kasher and Tim Ruggles from Georgia Tech and Sandia National Lab, who've helped with some HR-EBSD pattern analysis. So just to introduce the technology in our product, we've introduced what we call the Clarity EBSD Detector Series. And this is the first detector that's commercially offered that's been designed specifically for EBSD. And so it's a high sensitivity and a high fidelity detector that you can look at beam sensitive materials, you can get improved spatial resolution, you can get really high quality patterns. So it brings a new range of capability that we haven't been able to reach with traditional phosphor-based detectors for EBSD analysis. So just to schematically show this a little bit, this is a picture of a traditional, CCD or CMOS camera. So for the last 20-something years, we use CCD cameras for maybe 15 of those. In the last 5 years or so, we've transitioned to CMOS cameras for higher throughput. And with these cameras, the electron beam hits a phosphor screen that converts the backscattered electrons to light. That light is then transferred through some sort of optical coupling down onto the sensor, where it's then read out to form an image, which is subsequently used for image processing to determine the orientation and phase for EBSD pattern analysis. With direct detection, we're taking all that out of the chain. And this schematic shows it here, where we now directly detect the electrons and convert that to a signal, and then that signal is read out to form an image. And so it removes some of the inefficiencies that are involved in the conversion process from light or from electrons to light and then back to electrons in the sensor. We don't have to do two different conversions, and we don't have to transfer the light through the system. So it's a more efficient collection when we're using a direct detector. So this is a picture of the detector. So the sensor we use is positioned similar to a regular EBSD detector. So we come in, we tilt the sample to 70 degrees, as we see in the picture here, and we position the detector so it's around 20 millimeters away. The sensor size here is pretty typical, pretty close in size to a typical EBSD phosphor screen. So the geometry is the same, the ports are the same. And the way that the sensor works is this is what's called a hybrid pixel direct detector. So if we look at the schematic up here on the left, that means our active sensing layer here is on the top. This is where the electrons come in. I'm going to show a little animation. So they come in, they form a charge. That charge is then collected, and so the sensing material is bonded to the readout circuit. And so when that charge comes through, it's amplified. It goes through the readout circuits where there's some sort of thresholding to remove the noise. And if an input signal exceeds that threshold, then it's counted as a signal. And this happens for every pixel in the array of the detector. So what that means is we're able to get down to single event detection. And the way we filter it is we get rid of readout noise as compared to traditional sensors. So we have better sensitivity to events at low dose conditions. So that allows us to look at microstructures. So this, just an example, this is from a lower current map, but this is more of a traditional material. It's just a highly deformed iron powder, and we're mapping it at 200 picoamps, which is, an order of magnitude or 2 orders of magnitude less than typical conditions. But it shows we can do regular EBSD mapping with this technique. This is a very, a larger map in terms of number of points, where we see in the image quality map on the left, you can see some of the structure from the contrast is determined from the EBSD pattern quality variations. So you can see the cracks present in that map. You can see some of the subgrain structure that's present within the grains, and in the orientation map on the right, the colors are shown in this inverse pole figure map. The colors indicate the orientations that are aligned with the surface normal direction. So we can see within those grains that there's some variation in color that corresponds to the deformation structure that's been introduced during the cold pressing of the powder. So that's a pattern map of a material. Here's another one at 300 picoamps. This is a deformed platinum material, where we can see some of the deformed grains, again, have these variations in color. We see some recrystallized grains here. These are more recrystallized grains where it's a solid color. These are the deformed grains, and we can analyze these at low beam currents. But these are just examples of large maps where we can replicate what we can do with traditional detectors at lower beam currents. So what I want to talk about now is just a little bit of introduction to the EBSD signal, and as we go forward, try to explain why that's important for direct detection. So this is a live image, not a live image, a snapshot of an image when we're looking at multiple grains from a sample. And so what that means is we don't get an EBSD pattern, we're getting what we call a background signal, or that's the overall intensity gradient that's hitting the detector when we look at multiple orientations. And you can see the detector is what we call a quad detector. There's 4 different chips that are used together simultaneously. And when we're looking at it with no correction, we see that seam in there where we're joining those together. And so, and you'll see that the intensity gradient on the EBSD detector is not uniform. It's bright towards the center, and then it decays as you go out towards the sides and then towards the corners. So you can see it's sort of a radial type of an intensity distribution. And so that will just have some implications when we think about what's the signal level we need to analyze these EBSD patterns. So when we take this signal, and I drew a line profile horizontally across this and looked at the intensity profile across that line, which looks something like this. And that just kind of shows how the intensity across the sensor, varies by, over a factor of 2 in terms of intensity difference. And that'll vary a little bit depending on how close or far you've positioned the detector. But this is in a position where we get, sort of optimal solid angle for analyzing, both high and low symmetry materials. And so we see the shape of this in 2 dimensions. In a minute, we'll look at it in 3 dimensions, but there's this background signal profile. And when we put the electron beam into a single grain, we see a pattern that looks like this, where now we see the EBSD pattern. And so if you're not familiar with this pattern, the lines or bands that we see in that pattern correspond to different crystallographic planes in your material. And so the arrangement of those planes determine the orientation, and also the planes that you see also represent the crystallography of the phase that you're looking at in the microscope. And so for this pattern, if we draw this same line profile, what we see is that the intensity of those lines is essentially superimposed on that background signal. And so it's these little peaks and valleys across that background signal that define the bands that we're interested in analyzing for EBSD. And so the question comes up is, how many electrons, how low of a dose can we analyze and still get a usable pattern? And this, of course, will vary depending on the material we're looking at. So this is just an array of examples looking from lower atomic number to higher atomic number of the pattern superimposed on that background. And so you can see the 2-dimensional image, and then plotted in 3-dimensional space as well, where the z-axis is the intensity. And it's important to note that on the signal we're looking at here, we call it the raw signal or the live signal, the band intensity is typically only about 5 to 20% of the total signal. And that ratio depends on the composition. It'll also depend on the density, crystal quality, and surface condition. And I'll use that as a quick aside to mention that, no matter your detector, your quality of your diffraction pattern will always be influenced by your sample preparation and the quality of your crystal lattice. It's not, you can't buy a better detector that says I don't need to prepare a sample for EBSD, unfortunately. But the ratio of, essentially, I've called it sometimes, your diffracted signal to your scattered signal changes with material. So this is an example where this is looking at a lower atomic number material, silicon on the top, and then a higher average atomic number material for platinum on the bottom. This is a fixed beam current of just under a nanoamp at 20 kV, and different collection exposure times, as shown on the horizontal axis here. And one of the things we're able to do with this detector is we can count the number of electrons per pixel. So at these different beam doses, we show here the number of electrons on average per pixel. And remember, we do it like that. That means there's more in the center and there's fewer at the edges. And this is representing an average value. And we can see for any given time, the platinum will have more electrons than silicon. That's just due to a higher backscatter coefficient. And looking from left to right, as we dwell longer, we count more electrons. So our signal noise improves just from collection statistics. That's just a result of counting, the Poisson noise kind of thing. I don't know if that's correct. Sorry. When we talk about this being a noiseless detector, we're talking about we're cutting out sort of the electronic, the read noise of the detector. We'll still have statistical noise from the number of electrons that are counted. And so you can see as we count more electrons, the bands become more apparent to the eye, but you'll also see on these low dose conditions, we can see patterns that would not be visible at similar doses with a camera that did have read noise. And then what we usually do is we do a correction of the background. So we take that background I showed originally and we subtract it from the live signal to flat field the image. to get something that looks like that. And so this makes it easier for the computer to detect the positions of the bands, either through traditional Huff transform band detection, or we'll talk about some dictionary indexing stuff a little bit later in the presentation. And if we want to show it a little bit more, we can also start thinking about averaging frames. That just shows these a little bit more in general, but there is information content even in these low dose patterns. Okay, and so we get an idea that, you know, we're at a range here where we're in the, you know, 6, 8, 10 average electrons per pixel will give us an indexable pattern. So this is just a comparison of that. This goes back to our background subtracted pattern I showed from the original slide. Looking at that same line profile, this is now the intensity variation across that horizontal line. And we can see that there are plenty of electrons, even after background subtraction, or plenty of signals that show that we get a nice high contrast EBSD pattern. This is with 5,000 average electrons per pixel. Now, if we reduce the dose, this is dropping this down to 10 average electrons per pixel. So when I'm looking at this on my monitor, I can see the diffraction pattern. I can see it's not the same orientation that's shown on the left, but if you watch my cursor, there's sort of a main band coming through here. There's a band through here. There's a band through here, one through here, one through here that you may watch and think, boy, he's stared at these way too long. But you know, if the human eye can detect it, our band detection is actually very robust and can find this. But we're dealing with a very sparse signal. You know, if you look at the range through here, where we're dealing with 10 electrons. And if we look at this though, from our indexing, we can determine the correct orientation. We can determine that with high confidence. And so with these conditions of 10 average electrons, we can actually collect a map. So this is an example looking at, this is an additively manufactured steel sample with some deformation and subgrain structure. And so if we look at the orientation map here on the left, so again, these pixels are colored according to the orientation aligned with the surface normal direction. We see the grain structure very nicely. The black points here are points that we do not index with high confidence. So these are ones we say we would filter these out as suspect points. But you can see what's remaining is still 98% of the points collected are of high confidence. So even at these low beam dose conditions of 13 picoamps, 10 electrons per pixel, we're able to get a very usable map. And I'll also point out, if we look at our Prius map, this is what we call our Prius map, and the Prius map is where we use the detector, the detector itself as an electron imaging detector. So you can see the microstructural image that's formed simultaneously. There are some like specks of dust on the surface. So a few of these black points correspond to that. We can correlate that nicely. So we can go down to very low doses. And so that enables analysis for beam sensitive samples, and we'll see unparalleled spatial resolution. And so with this year, what we've launched is what we call our Clarity Super Detector. And so what we wanted to do, as we started with this low beam current performance, is continue to extend the performance, and now we can go down to 3 kV with efficient operation. And I'll try to show some advantages of that. So this is just a little chart showing the improvements we were able to introduce with the Clarity Super. So the blue line on this chart, let me explain the chart first. This is the time to equivalent signal for a velocity, a phosphor-based detector, and then the Clarity Plus, which is our first generation Clarity, and then the Clarity Super, which is our second generation. And you can see the blue line shows that at lower voltages, the phosphor-based cameras become less efficient. And that's primarily a function of how the phosphors work. The Clarity Plus worked well down to about 7 kV. Then it started to have a drop off in efficiency and a drop off in performance at lower voltages. And so the efforts we put in were to optimize the sensor itself to be able to extend performance down to 3 kV, and that the performance was pretty constant in terms of sensitivity across that voltage range. And so what that opens the door is to say, can we go to lower voltages efficiently compared to previous detectors. And this is just a little schematic. It's the same distribution there here. And it shows there's a pattern at 20 kV. There's a pattern at that 7 kV threshold. And now we can get down to 3 kV. So we still see bands. They can still be detected with the Huff. They can still be used with dictionary indexing. But we see, up to 60-fold times improvement in performance at these lowest energies. So it really starts to think about low voltage EBSD as a difficult acquisition parameter. And so you can think of some easy things we can use this for. Is that running at lower beam doses and lower beam voltages can do things like reduce charging and drift. This is just an example. This is from an alumina ceramic where, traditional conditions of 30 kV, 5 nanoamps here on the left, get charging. We run something at 12 and 1 nanoamp, that charging goes away. And so we can help minimize having to use conductive coatings or low vacuum SEMs and improve spatial resolution through this. And this is just a schematic showing, when we talk about spatial resolution, maybe what we're going to be able to do. So this is just showing the number of electrons per nanometer square for different interaction volumes on the surface of a tilted sample at these 3 different ranges, 20 kV, 7 kV, 3 kV. And you can see that by dropping voltages, we're able to reduce that interaction volume significantly compared to a higher voltage. And so to show this sort of on the surface of the escape, this is this is a chart or some figures showing the backscattered electrons that are escaping a tilted surface from a Monte Carlo simulation as a function of energy and a function of position of the surface. So the 0,0 point is where the beam enters, and then the warmer the colors, the closer to the incidental energy that's being represented. So for EBSD, the patterns are primarily generated by the near incident energy electrons. And so, kind of looking at the redder colors to get an idea of what's the interaction volume for EBSD pattern formation. And so I'm going to put these so they're on the same scale. Again, from left to right, we're varying atomic number here, going from silicon, sort of a low end, nickel mid-range, and platinum at high end. And you can see 2 different trends. From left to right, as we increase atomic number, our scattering volume, our interaction volume and spatial resolution will decrease. And as we decrease the voltage, they decrease as well. So we can get a feel for those differences. And if we look at it more numerically, we see this type of an estimate of what the interaction volumes are. We are tilted so that our spatial resolution in one direction is typically a little bit less than it is along the direction of the tilt. There's more spread in that direction. But at lower voltage can see 3 to 4 times improvement in the non-tilted direction and 4 to 5 times improvement in the Y direction. So this detector is more sensitive. It's more sensitive for both currents and energies. So what can we do with this? So the application we've really keyed in on are these Perovskite solar cells. So these are Perovskite's a term that it's a specific crystal structure that comes from a mineral, but you'll hear about these hybrid Perovskites now. It's becoming more and more of interest because they show a lot of potential for high performance and low cost manufacturing. So that's obviously a very good combination to help with renewable energy, and there's been rapid improvements in efficiency. So the challenges are, one, improving the efficiency, but also improving the stability. So there's a lot of work going on in understanding essentially the microstructure. So to do this, you need the capability to characterize the microstructures to understand how that affects efficiency and stability. So as kind of an overview, we've looked at a wide range of, again, Perovskite is sort of a catch-all term. There's a wide variety of materials that fall under this umbrella, and a wide variety of microstructures. So this is just a little array of 4 different samples that we've looked at with a Clarity, with different kind of structures. So you'll see in these, some of them are smooth grains, some of them look to us more like faceted grains. Some of them look like, I call them coral grains, where they have sort of porosity looking stuff in it. There's some brighter particles, some brighter plates, and generally you can observe some what you'd be called grain structure. And in these materials, you'll have a range of compositions with different elements in there, varying ratios of organic to inorganic compounds. And the important thing is, even to look at these with SEM images, you need to look at these with very gentle beam dose conditions. You can actually watch the beam damage occur. So for EBSD characterization, we need very high sensitivity, and that need increases as the beam sensitiveness of a sample increases as well. So one of the things we wanted to look at is this is for one Perovskite. We wanted to look and say what currents are needed to obtain indexable patterns from a Perovskite film. This is looking, we're adjusting the beam current, and it's not a strictly objective measurement, but trying to find the areas on these microstructures that produce the best patterns. This is comparing the clarity and the velocity to give an idea of saying what sort of improvements do we see, especially as we go to these low beam dose conditions. So this is just showing that the clarity we're running at 5x5 binning. Cumulative means we're summing things up. The velocity we are running at 4x4 binning. The pixel resolutions of these are slightly different, but in general we're ending up with about the same pattern size for the analysis. So we see a curve that looks a little bit like what we saw before, that at higher beam energies the clarity is more sensitive, but as we go to lower beam energies, the improvement differential improves with the clarity. And so this is on one scale. This is kind of showing it out to get rid of the outliers there at the low end, to show that it improves here. And so with the clarity, we could go down to lower KVs and get patterns much more efficiently. And so to show these are just some examples. So this is going down. This is a pattern at 3.5 kV we can index, 4 kV, 5 kV, 6, 7, 8, and then jumping up here, jumping from 9 up to 30. So you can see the patterns in general are pretty low quality. They're not patterns from a nice, easy, platinum nickel sample. They're weak patterns in general, and they will disappear if you leave the beam on them for a significant length of time. So they're a very challenging sample, but we do get results and patterns from these. So I wanted to show an example from actually a pretty difficult film and show what we're able to learn from it. So this is an example just showing the degradation we can see. If we image an area, you can actually see the cracks that start to form. And if we go to lower, gentler, this is going from 20 kV to 5 kV, that we're able to image an area without seeing the cracking, but we will still see some degradation in the image, the EBSD pattern quality. So the need is to be able to say we need to use a gentle dose and acquire the pattern before the structures are destroyed from a crystallographic point of view. So this is an example. This is from a methylammonium lead iodide-based Perovskite. And this is just looking at the SEM images. So you can see the microstructure here at 2 different magnifications. And these were collected as sort of reference images to get an idea of the structure. And for even the images, it was collected at 8 kV and 50 picoamps. In this case, 20 pascals low vacuum condition. And you can see the grain structure. There's a little bit of porosity in the film. And then there are these brighter white crystals that are protruding out of some of the grains, but not all of the grains. And you can also see that some of the grains are more contoured or ridged than others, and that the plates are crystallographically aligned or well, let me put this, spatially aligned at this point. We'll find out they're crystallographically aligned within particular grains. So this is again the image here on the left, and remember now we tilt our sample to 70 degrees for the EBSD analysis. So as we do that, these grains have some topography. So if we think about the EBSD detector and where it's positioned, as we're positioning the beam along this topographical surface, there are only certain faces that, one, are oriented towards the EBSD detector, and two, we can also hit with the EBSD, with the electron beam to generate a pattern. So essentially, it's not the ideal flat surface we would want for EBSD analysis, but that topography means there's only certain parts of the map that are going to produce, or certain parts of the image that will produce a pattern and produce quality data in a map. So that's a function of the topography. And if we analyze the structure, we see that the small white crystals, they produce pretty nice patterns. You can see those there on the left, distinct bands. We can index those, find the orientation pretty straightforward. And when we go across and we do our first mapping of the surface, we see we can measure the orientations pretty nicely of those smaller particles, and some of the larger grain edges will also produce patterns. But you can see we do see clustering of the orientations in this IPF map here on the right. So there are groups of colors that are together, indicating that we are measuring something from some of these small particles that are the same orientation. We kind of get an idea of how these correlate with the grain structure we can see in the image quality map. And these were collected down at, this is 10 kV, 40 picoamps beam current. And so what we can do is something that we call NPAR. And this is a patented approach that we developed, that we take all the patterns we saved during collection, and for each pattern on the measurement grid, we average it with the neighboring pattern. So this essentially helps, improve the electron dose per pixel by, averaging spatially with the adjacent neighbors, and that allows us to essentially improve the signal to noise of the pattern. And so when we have these weak low dose signals, we can improve the indexing to look something like this. So now our grain structure is better defined in the image, or in the Prius map, and we can see now we're measuring more of the grain areas. And again, these are on areas with spatial orientations more suitable for detection with the geometry of the EBSD detector. And we can start to see, these particular grains that are being resolved. And then, kind of extending this over a large area. So this is an area that's 170 microns by 140 microns. This is looking again just at the original data, the non-NPAR data for sort of the smaller particles. Again, you can see the general trend for the grain shadows, for lack of a better word, of where things are oriented, and we compare that for the orientations. We see that those small grains produce a preferred orientation. You see that there's a 111 orientation oriented with the sample normal direction, with these peaks here in the 001 showing kind of the orientation that's developed in that film. So these are essentially, these are what are pole figures that show the spatial alignment of these 001, 110, and 111 orientations. And so we can see those for the white crystals. And then if we apply our Prius map, again, we start to resolve the structure more. We start to see more of the grain structure that's visible in the detector. And if we look at the pole figures for this, we see again that these have the same orientation. So we can see it's a 111 sort of center, sort of these peaks in the 001, indicating that there's an orientation relationship between these small and large grains and how those are growing from the underlying grain orientation up to those smaller crystals. They have a growth relationship. It's not a random orientation growth. So it's a really cool example from what's a pretty challenging material. We have to use low dose. We need to use a clarity, high sensitivity. We have to use NPAR to extend what we can see with those low dose patterns. So we can get some very useful information to understand how those grains are developing. And at the same time, we can get things like grain size measurements that are traditional with EBSD analysis. So it helps to understand how do these microstructures change as you change the chemistry and processing parameters of these perovskite films. So that's one beam sensitive application. The next one I want to show is a biomineral application. So this is a shell that's where we see it's a calcite aragonite transition, and calcite and aragonite are both calcium carbonate phases. So chemically they're the same, but crystallographically they're different. So this is the image quality map here. On the we see down in the lower left there are these calcite pillars. Up in the top right there's the aragonite planar nacre, and collected at 12 kV, 800 picoamps. And we can look and say, here are the orientations that are present. So for the orientation map for the combined phases, there's two different triangles that are used to represent the orientation for the two different phases. But you can see they both are red. So for the aragonite, it's an 001 orientation. For the calcite, it's a basal 001 orientation with some changes in some of the smaller structure. But overall, you can see it's pretty strongly preferred orientation. And looking at the different phases, we see the calcite pillars produce some patterns here. We see that the aragonite plates produce some patterns. And in that transition region, we see some weaker patterns. And so if we apply our NPAR filter again, you can see the improvement we get in the patterns. They're very a little bit easier to index. And we see the indexing there on all three regions nicely. And we can go zoom in on some of these areas. This is looking at the transition area in a little more detail, where we can see that between these calcite pillars, there are smaller aragonite crystals that are forming. And so this just shows the phase map of that. So we can see here's the calcite, here's the aragonite, and then we start looking at the orientations of just that aragonite that's formed. We can plot that out as a pole figure, and we can show the little crystallographic unit cell here, looking at the 001 axis and how it's oriented. They're pointing out of the screen. We can see how the crystal's oriented in space, sort of pointing in the same direction of those larger calcite pillars. And then this is another biomineral application. This is one that it's a garden snail shell. And I show this one because it was to prepare it for EBSD. It was cross-sectioned with a Gatan PEX2 ion mill. And you can see the patterns there are nice. You get a multi-layered structure with a columnar base and a fine-grained cover. The entire structure is, again, calcium carbonate, in this case, just aragonite. So this is the EBSD image quality map here. This is after peeling off the top layer. The gray areas we see in some here are some of the residue of the organic material. But we can look at the orientation map. Again, we see it's all a particular strong texture and 001 orientation. We can show it in the pole figure showing similar clustering. And then if we look at a fracture surface across this, we can see that the surface normal orientations, again, are all 001. They're pointing out of the screen here. But if we look at the in-plane orientation, we see that there's a transition. So we can see this spatially. So the A1 and A2 axis are relative to how we put the shell in, but it corresponds to sort of the direction shown here. So the blue grains are ones where the 001 orientations are in plane in this direction, and the green colors are in an opposite direction. So this kind of shows a schematic here of how things are oriented, along with some of the platelets that can be observed in the columnar structure. So those are a few different applications where we're using low beam doses to work with the the weaker patterns, but can still analyze it. The other advantage we get with the Clarity is because we don't have to deal with a phosphor and optics, we remove blurring effects that are present with traditional systems, so we can get some very high quality patterns with very high dynamic range. So this is just an example from silicon, and you can see that the amount of detail that's present in there is high. So if we look at this a little more numerically, this is looking at a band, a common band between a pattern here collected with the Clarity and collected with a phosphor-based system on here, selecting that band and then doing a line profile across this normal to that band, just showing that the contrast in the band here, essentially the peak to trough distance here is higher with the Clarity, and the slope of that line profile is sharper. So we get higher contrast and sharper diffraction bands. And of course, we're also able to count the true electron intensity across the field of view. And so we get better, sharper patterns as we're looking at pattern quality level exposures. So going back to an example like this, what that means is it helps for band detection can improve. So this is just showing from that deformed powder material. This is what we showed this earlier, where we looked at it sort of as a general view. We can look at it with some different map types that are designed to look at the local misorientation that's present in the microstructure. So on the left here, what's called a kernel average misorientation map. So the colors here are just showing what's the small misorientations that are present point to point in the material. And we can see our CAN map is essentially we start to see subgrain structure and walls present within the larger grains within the microstructure, and then near some of these boundaries we see the accumulation of some of those low angle misorientation. We can also just see this structure what's called a GROD, or grain reference orientation deviation map, where we can show these orientation gradients relative to the average orientation with high precision and minimal noise. And we can show it on a single crystal. So this is a map that generally should be all blue, but have gone in and introduced a small indent to introduce some deformation in the material. So here on the left, we're looking at a misorientation map, a low angle boundary map cam, and a higher degree value, looking to say how are those counted. So we can see that these deformation structures that are introduced with high fidelity with traditional EBSD pattern indexing. And then we can extend this to what's called HR-EBSD, or just to help clarify the confusion, pardon the pun, high angular resolution. We're not talking about spatial resolution or pixel resolution or mapping resolution, but high angular resolution. How small of a difference can we detect with EBSD patterns? So this is an approach that was developed by Angus Wilkinson and his work in research groups. But the idea is we take two EBSD patterns, one which we'll define as a reference pattern, another that's our experimental pattern, and within these we define a number of regions of interest. And though this is just a schematic showing a few regions, but within each region of interest we compare the two in essentially Fourier space. And so we're looking for this cross-correlation peak and see how it moves in this region of interest. And when we then do it for all these ROIs, we start to get an idea for what are the shifts present in the pattern. That cross-correlation can find shifts at the sub-pixel level. And from all those, that distortion field, we can calculate a displacement gradient tensor at the end. And that can then lead to higher precision and some strain analysis of materials. So this is just an example for that same indent material. We're looking now at a high resolution cam map, so we can see it filters out noise. We see this with a little higher precision, but we can also start picking out stresses and strains in different components of the tensors. So you can see here how now we can start to get in the blue areas, it's essentially a negative stress, and in the red areas, it's a positive stress. So we get some idea of is it compression, is it tension, in that we don't get with typical EBSD, but we can resolve with HR-EBSD, and with the Clarity detector helps to improve precision. And that's can also be extended to polycrystalline materials. So this is an area within an additively manufactured material. So they get some of their properties from the subgrain structure that forms in these grains. So we wanted to come and take a look at this. So what we're seeing is with a standard EBSD inverse pole figure map on the left, it's difficult to see, well resolve the structure. This looks like mostly one grain. And so when we apply the HR-EBSD analysis, we look at it with the HR-CAM map, we start to see some of the structures that are evolving in there. And we can represent this in a number of different ways. One way is with what's termed a GND, or a geometrically necessary dislocation map. This gives an idea of how many dislocations are required and to create the amount of misorientation and lattice curvature that we detect with HR-EBSD. And so this shows that you can see the high angle boundaries, and you can see the lower angle boundaries in the structure. And then if we look across some of this, we can again start to see for the stress of when it's in tension and when it's in compression in terms of the stress state that's present in the microstructure. So understanding that just helps say, how can you engineer these materials better to take advantage of those strengths? We can also use the quality of just the image in general. That with the Clarity, we can actually see some of this dislocation cell structure that's present with some of the different maps we generate in terms of image quality and Prius maps compared to a bright field TEM image. You can see how we get some of that same type of contrast. So this can help guide where you can take some of the HR-EBSD measurements from. And then for pattern information, one of the things we think is cool is we know as the beam comes into the sample and generates sort of a point source, as the electrons scatter back out, the patterns that come into the center have a smaller path distance through the material than those that go towards the edges and the corners. As the material interacts with as the electrons interact with material, if your dislocation deformation content is higher, you're going to get more diffuseness and blurring from the increased interaction with that deformation. And so we see patterns where it's sharp in the center and more blurry towards the edge. And traditionally, we're sure to say, is that an effect of the detector, or is that real microstructural information? Well, we know now it's not a phosphor effect, it's not a lens effect, it's not an optical effect. It is an idea of the deformation present from the local source in the material. So this is just another example where the patterns are sharp in the center and more blurred towards the edges, that we are interacting with lattice defects, and we see an effect from that. And so that leads to say, are we going to be able to start to extract some information from that? And the way maybe we're going to be able to do that is through pattern simulation and comparison. So that's sort of what we can see here. This is just an easy example from a pretty pattern, where just showing how we can simulate similar patterns to what we collect experimentally. These are dynamic diffraction simulations comparing against the Clarity. And so there's some applications of things like, well, I'm going to show an example of resolving what's called pseudosymmetry, to where the patterns themselves are very similar, but can the small subtle differences be detected with a Clarity in this sort of an approach. Oh, sorry. So dynamic simulation, what we need to do is we need to be able to create sort of these more accurate pattern simulations. So the approach that we use is developed by Mark DeGraff at Carnegie Mellon University and his research group, where the first thing we do is we create a Monte Carlo simulation of the electrons within the crystal structure to get an initial starting point. And then we construct the master pattern of the orientations and basically we go from what's called the sphere projection here to a square projection via a lambda projection. But we're essentially simulating all the orientation space here and can project that. And then once we have this for a material, then we add our EBSD detector geometry and the crystal orientation of interest to extract the section of this orientation space that represents what we should be seeing with the detector. So that's how very quickly we create a simulation. And so when we talk about dictionary indexing, what we do is we take that orientation space and we create patterns that are sampled through that orientation space. And so we simulate an array of patterns and create a folder of those patterns, and we just call it a dictionary. It's what we're going to look up for comparison. And so, there's some subtleties for how we sample orientation space effectively with this, and we have webinars, and Mark has papers about that. But the important thing is, once we have the dictionary, from this general perspective, is we take a pattern, we compare it to all the patterns in the dictionary, and then we find the best match. Okay, and then we use that best match as our orientation and our phase solution if we're looking at multi-phase matching. So why is this important, and why do we use it? We look at the patterns here. This is the Huff-Bakes indexing. As the pattern quality decreases, you can see that we get more noise in the EBSD results. This is just from the band detection. Starts to have more and more trouble as your signal to noise decreases. As it progressively increases, it gets to the point where the Huff is just finding noise. And so, I showed earlier things like NPAR can help improve signal to noise, but that comes with a spatial averaging effect. Where dictionary indexing, there's enough information content still present that you can see really down to about here, we're pulling out the correct microstructure at this point, and then this becomes a little noisy, but you can see that it extends the performance of what we're able to index beyond what we can do with the traditional Huff indexing. So that's very exciting. The trick is these dictionaries can get pretty large. So this is showing the number of patterns in the dictionary. And the axes here are one, this is the crystal symmetry. And so then there's different symmetries, different point and space groups within these, but it gives an idea of this is high symmetry to low symmetry. And then the angular resolution, how finely are we sampling orientation space? So as we start to get into the angular resolutions that are our most interest for EBSD, and the symmetry decreases, these dictionaries get very, very large. And even as we decrease this for a cubic symmetry at smaller values, they're a large number of files we have to compare against. So the way to make this more efficient is what's termed spherical indexing. So I showed earlier the EBSD pattern itself was on a sphere. So we can project the pattern that's collected onto the sphere and again find the best fit. And the fit's found through some spherical harmonic functions comparisons. It's like doing an FFT on the sphere is an easy way of thinking about it. And the best match corresponds to the orientation of the experimental pattern. So what this means is we don't have to pre-calculate a discrete dictionary. It becomes a lot faster of an approach. And then we don't have to do a refinement step. I didn't talk about the refinement step, but that helps to improve the precision of the dictionary indexing. And so this is a slide that I really like because it shows, why we're doing things and the advantages of going to spherical indexing. So this is a shot peened aluminum surface where we see with the Huff indexing, HI's Huff indexing, we're able to resolve some of the larger structure, but as we get into the shot peened area where there's more deformation and the grain size becomes much smaller, the Huff indexing starts to have more issues. The dictionary indexing does well resolving that. You look and just compare those two and it says, yeah, dictionary does a good job. And then these are what's termed bandwidth that helps define how precisely we're using those spherical harmonic things to find the matches. And you can see that even at a 41 bandwidth, the structure is pretty nice and it improves as we go through here. And it gives an idea here of the sort of time improvements we can get. So dictionary indexing, 85 hours for this data set. And then we can drop that down to as little as under 40 minutes with these bandwidths here that resolve the microstructure very similar to what we'd see with dictionary indexing. So dictionary indexing should be a very exciting way to index some of these tricky applications. But then again, to lower quality patterns, we can apply using Clarity in the high quality patterns for analyzing what we call pseudosymmetry. And so this is just an example where this is a barium titanium oxygen compound, where if you look at this crystal structure, you'd look and say it looks like a cube. And if you look at it, it's actually tetragonal, but the A to C, the A axis and the C axis and the A to C ratio, essentially it's a very small distorted cube. So whereas your eye would look and say, yeah, it's hard for me not to see that it looks like a cube, even though it's just slightly not a cube. We see the same issue when we look at the EBSD patterns. If you rotate to different orientations, the EBSD patterns for these different, they're non-symmetrical orientations, but they look symmetric. So that's why we call them pseudosymmetric. And so if we look at the pattern in general here, the black symbol represents true symmetry operators for the material. The red symbols show the pseudosymmetric axes. So there's quite a few, and every orientation you have can have a number, 6 different pseudosymmetric variants. And so we have to find the right orientation to match, but we're going to have to match it against some other ones. So this is the microstructure from a sample from ETH Zurich. So if we look at it with the Prius image, Prius again is using the EBSD detector as an imaging detector. We see it provides us some nice contrast. So we see some porosity, but we also see this lamella structure present within some of the grains. So pulling 3 different discrete patterns out, we can see the 3 different orientations that are present in the lamella. And with the Clarity pattern sort of on a cycle there, you can see that these just represent small shifts in the pattern. So we can visually see these shifts. And so can we accurately map it? So we try to do this with traditional Huff indexing. It sort of starts pulling it out, but it's not consistent. And so what we wanted to try to do is if we apply spherical indexing to this, we see that it does improve the indexing result on the material using the spherical indexing approach. So it's kind of an exciting new application for combining the spherical indexing and the dictionary indexing and the pattern simulation from what we call our OIN matrix package with the pattern quality we can get with the Clarity. Excuse me. So as a summary, direct detection provides high sensitivity and high fidelity performance. It enables beam sensitive analysis, beam sensitive sample analysis that are especially on materials that are difficult to impossible to do with traditional EBSD detections. And then we can resolve some pseudosymmetry issues by using it in conjunction with something like OIN matrix. Excuse me. So with that, I'm going to say thank you. I'm going to remind you can submit some questions through the question pane, and so I'm going to take a look here at a couple that have been submitted. So the first question says, does the low voltage work require different sample preparation? And so that's actually a very good question, because the answer is yes for a couple of different reasons. First, because we're running at lower voltages, we are a little more surface sensitive. The electrons are coming from closer to the surface, so your polishing or your crystal quality, you want it to be representative of the true structure. So any lattice damage that's introduced during preparation, needs to be removed to a finer scale than if we were doing it at higher voltages of 15, 20, 30 kV. The other thing that's tricky at the low voltages is you are a little more susceptible to carbon contamination, and that will at lower voltages, local carbon contamination can attenuate the signal a little bit more. So you have to you make sure your sample is a little clean. Plasma cleaners are applied to the problem to help try to address that. There's another question in the number of pixels in the detector. So the detector itself has 512 by 512 pixels that are defined by four different quads that are put together to get the 512 by 512. And again, that was designed to the size, between the size of the number of pixels we're using, the size of the pixels, puts it into position similar to a regular EBSD detector. And then there's is dictionary indexing controlled through the software, or is it something that the Clarity detector does automatically? And so right now it is not done automatically. It's dictionaries through the software, but it's done after the initial data collection. And so we have a module in our OIM analysis software that you save your orientation information, your mapping information, you save the saved patterns, and then it couples that information to the pattern simulation as part of the analysis routine. And so there's part of this question says, can it be used with an older detector? Yes, it can. I was going to say something about it. It's all coupled through the analysis software to make it easy from that perspective. So go up in this one. Sorry, I'm making this a little bigger. There, I can see stuff. So I have a question here. How do we fill in the cross between the segments? I don't know the exact algorithm, but it's trying to look at, balancing the, the average intensity across that. And we basically have a way to you manually adjust it. Right now, it's just looked at, visually trying to get to have it the same gray level across that. So you do for something like HR-EBSD, trying to, you don't want to put your ROI on that because it'll fix your cross correlation. So at the point right now it is not random noise, but just an average value between them. And there's one here. Is there a lateral resolution limit, i.e. a step size, or is it dependent on the sample? I mean, in the end, there's some limit in terms of, whatever your beam conditions create as sort of your interaction volume limit, which will fundamentally limit what you can do. But yes, it will be dependent on the sample, and it will also depend on if you're doing, traditional EBSD or using this detector for transmission EBSD or transmission Kikuchi diffraction. We've done step sizes at 1 to 2 nanometers on specimens where it's appropriate, but it's really sample dependent often of what your step size selection would be. So there's a question here regarding EBSD. What can we do to have better indexing on highly deformed samples? And so, I mean, that's where there's a few different approaches. One, indexing with the dictionary indexing, like I showed on the shot peen surface, that will help to improve your indexing. And that's trying to address the quality of the pattern that's coming out of that. The other thing we can do is operate at lower acceleration voltages, so your electron beam is sampling less of the deformed crystal essentially, and so the pattern you do get from that will have sharper information. It's a little bit better pattern as you decrease the voltage, and that's an area where the Clarity, because it can still run at lower voltages more efficiently than a phosphor, can help get some performance in that regard. All right. Well, I think we're about at the time. I can't see if there's other questions through here, but if I didn't answer it, I will address it offline. So with that, I will say thank you very much for your attention. Please contact myself or EDAX if you have further questions, and thanks again.